So perhaps before I start the lecture, I should just remind you of formulas. We're looking at graphs, connected graphs. So we'll continue on this topic for a while. I'll just remind you Euler's formula, which is the number of edges minus the number of vertices equals what I call the loop number minus 1. I think that's correct. So this, you can take this as a definition of the loop number. So last time we introduced these polynomials. The graph polynomial or Kyiv polynomial. And I'd like to talk about some properties of these polynomials for a bit, and then we'll go back to some sort of number theory and start putting things together. So the first property is very simple but important, called contraction deletion. So I remind you the definition. Psi g was the sum of spanning trees then for each spanning tree you take the product of variables not in the spanning tree. So now let's take any edge in the graph. And there's a recursive way to compute psi g. And psi g equals alpha g psi g minus edge e plus psi g contract edge e. So it's obvious from this that it's of degree at most 1 in every variable. If you pick a variable, you can ask what is the coefficient of that variable and what is the constant term. And they can be interpreted as polynomials of the same type for different graphs. So g minus e is the graph where you delete edge e. So the graph might not be connected, but that's okay. You can still apply this definition, and if the graph is not connected, this will just be 0. So actually, I don't need this assumption. Sometimes, I mean, if it's not in general, this will be the number of connected connections. But these things are not interesting for not connected graphs. Then g double slash e, this is my notation. So it's two possible things. It's contract the edge e if e has distinct endpoints. So if you have an edge like this with connecting vertices v1 and v2, then what you do is you delete edge e1 and you identify v1 and v2. Now if e does not have distinct endpoints, then we just define it to be the empty graph. If e does have distinct edge points, so it's what's known in physics as this is called a tadpole in physics. Baby frog, it looks like a tadpole. Okay, so then let's do an example of this. So if G is this graph, I'm going to look at this graph a lot today. 1, 2, 3. And E is edge 1. Then psi of G. So there are only 3 spanning trees. There's edge 1, edge 2, or edge 3. So if I take edge 1, the complement is edges 2 and 3, so I get alpha 2, alpha 3. If I take edge 2, I get alpha 1, alpha 3. And if I take edge 3, I get alpha 1, alpha 2. But this is also equal to, if I pick edge 1, this is alpha 2 times alpha 1. Sorry, it's not. It's alpha 2 plus alpha 3. Alpha 1 plus alpha 2, alpha 3. And this here is the graph polynomial of this graph. 2, 3, which is the graph G where I delete, I remove edge 1, and here the constant term is G. This graph, which is, this is the graph obtained where I contract edge 1. And so this is an illustration of this. And this is very easy to prove. So the proof, let's first take E not a tadpole, and we'll see the proof is the same in fact. And so this side is the sum over all spanning trees, and so we look at the set of all spanning trees. And a spanning tree either contains this edge or it doesn't. So this is in bijection, well, it's equal to the disjoint union of spanning trees T with E, an edge of T, disjoint union spanning trees with E not an edge of T. Now the set of spanning trees which contain E, what we can do is we can contract E, so that you can show that this is a bijection with the set of spanning trees T contract E of G mod E. So given such a spanning tree, you can contract it to get a spanning tree of the quotient. And conversely, given a spanning tree E, you can just put back the edge E. And here you get spanning trees which do not contain E. It's the same thing as spanning trees of G minus the edge E. So that's the idea, and then it's if you work with the definitions, you essentially get this formula. And in the case where E is a tadpole, it's essentially the same proof, but you notice that in fact a spanning tree can never contain E, because it would not be a tree if it contained the edge E. The edge E contains a loop. So it's an easy exercise to deduce this from this simple idea. Right, so that's a basic identity that's important for combinatorial applications. There are many combinatorial invariants that satisfy this kind of contraction deletion. The most famous is something called the Tut polynomial. This is something slightly different. It's not very efficient for calculating psi. It creates lots and lots of terms, but it's an important feature. Okay, so the next thing, next property of graphs of psi g I want to mention is very important for geometric applications. So that's graph Laplacian. Now I'm going to take a very elementary point of view, and at the end I'll explain there's a very, very short way to define graph Laplacian, but I'm going to do it very explicitly first. So I don't want to assume any so for this, let's take G connected. And we, as usual, we're going to number the edges of G, and we're going to choose an orientation on each edge. Choose any orientation on each edge. So as I go along, I'm going to do a running example. So we'll do the same graph. This is going to be our graph. And we're going to number the edges as before. And I'm going to orient them to the left. Okay, so the next step is to choose a basis C1 CHG of independent cycles in G. So each CI is an element of Z to the set of edges. I'll just put blue. So here's our graph. So the first cycle we could choose this loop here, C1. And the second one, I want to choose this one. So in typical fashion, I've done something completely different from what's in my notes. That's okay. So here we have so C1. C1 is E1 first, and minus E2. And C2 is I want to go around. I want it to be opposite. Otherwise I'll have strange signs. So C2 will be E2 minus E3. Ultimately, these choices won't matter. And for now, we're going to make lots of choices. You can choose any other. For example, you could take the big circle, you'd get E1 minus E3. Okay, so now we let HG be the HG by number of edges incidence matrix. So incidence matrix normally means something slightly different, but it's the same idea. I don't know what to call this. So HG of G. So HG of I, J equals the coefficient of Ej in Ci. So in our example, it's going to have 2 rows and 3 columns, so we can index the rows by each cycle, and we index the columns by each edge. And C1 is E1 minus E2. E3 vanishes. E2 minus E3. Now we let DG equal to diagonal e.g. square matrix where DG ij is delta I, Kronecker delta ij e I. Alpha ei, sorry. So in this example we have so finally, then we say a graph Laplacian matrix, because it depends on choices. It's not unique. If we change basis, we get a different matrix. So with these choices, lambda g equals hg dg hg transpose.
Hg transpose yours.
The dimensions?
Yeah, I think it's okay.
It's wrong.
Yeah, I think it's okay. So in this example, let's do it. So it's 1, minus 1, 0, 0, 1, minus 1, alpha 1, alpha 2, alpha 3. 0, 0, 0, 0, and then 1 minus 0. So this equals 1 minus 1, 0. Okay, so can I do this? This is alpha 1, 0. Alpha 2, 0, minus alpha 3. And at the end we get a 2 by 2 matrix, which is alpha 1 plus alpha 2 minus alpha 2 and minus alpha 2, and then alpha 2 plus alpha 3. Okay, so this example of this matrix is, if you can try to remember it, because on my talk on Monday, this is going to parameterize one of the Voronoi cells for 2 by 2 matrices. It's going to be, this graph Laplacian is very important in tropical geometry, monomer space of curves, all sorts of things. So this is, graph Laplacian is some sort of tropical version of Ardell-Jacobi now, if you know what that means. But this is very important. So some couple of comments about this graph Laplacian matrix. So once you've done a few examples, you can do this quickly, because you can see that I just deleted it. But see, the first cycle had edges 1 and 2. So just the sum of the alphas for that cycle. And the next diagonal entry is just, the second cycle is E2 and E3. So it's alpha 2 plus alpha 3. So you can just write down the diagonal terms from each cycle. And then the off diagonal is sort of the overlaps. You just see where the, look on each row and each column. And this element has an alpha 2, this has an alpha 2. Maybe that doesn't help, but if you do a few examples, you end up being able to write down a formula quite easily without having to compute all this stuff.
So would the change of alpha 2 change if we took the other cycle?
Yeah, so I was just about to say, so of course this depends on choices. That was my next comment. Depends on the choice of cycles, the choice of basis of cycles, and the orientation. So the orientation just changes some signs. It's not very important. Changing the cycle basis is like multiplying on the left and the right by a change of basis matrix, because we've changed the basis of a vector of a Z module, if you like, the vector space. So it's like multiplying by a matrix.
Just like conjugation.
By conjugation. So this is, another thing I forgot to say. So this is, it's obviously symmetric. So it's symmetric. And so the change of basis formula is lambda G goes to P transpose lambda GP if you change cycle basis. So P will be in G, L, H, G, Z. Change of basis matrix for the cycles. So that's the first comment. What else did I want to say? Well, let me maybe just continue with this. Oh yeah, and it's also a positive definite matrix. It defines a positive definite quadratic form, about which I'll say a lot more on Monday. And so from this fact, from the fact that if you change basis, you just multiply by P transpose of P like this. The determinant of this matrix is well defined.
Maybe SL.
Sorry?
P in SL.
SL or ZL? It's possible to change.
Oh, it doesn't matter. But
for transposition.
No. You can always take transposition, but no, it will in practice be. Well, I mean, no, you could have sine minus 1. If it was a 1 by 1 matrix, I could just multiply my cycle by minus 1. It's a GL. So the determinant is plus or minus 1, but the determinant is well defined because you have det lambda G equals det P squared. Det lambda G, and this is det P is plus or minus 1, and so det lambda G is well defined. And in fact, so the fact. This is the theorem that the determinant of this matrix is precisely the graph polynomial. This is an important fact. And it follows from, it's sort of equivalent, but not completely, but it's essentially equivalent to what's called the matrix tree theorem. Which is a famous theorem in Kontsevich. And this is a variant of the matrix tree theorem. So let's do this example. Let me put it here. So the determinant of alpha 1 plus alpha 2 minus alpha 2 minus alpha 2 is alpha 1 plus alpha 2 alpha 2 plus alpha 3 minus alpha 2 squared, and it equals alpha 1 alpha 2 plus alpha 1 alpha 3 plus alpha 2 alpha 3. Now if you're a bit more sophisticated, I'll be very brief. What you can do, instead of doing all these choices, making all these choices, you can just say we define a quadratic form so that's a symmetric bilinear pairing on this space by declaring that the product between EI and EJ is delta IJ alpha EI. In other words, the edges are orthogonal and the length of each edge is alpha. That gives you a quadratic form on this space, and you just restrict it. You can restrict a quadratic form to the subspace H1 GZ. If you know what this means. This is the vector space spanned by the cycles, essentially. So this is a very efficient way to just do everything I said. It's really equivalent. Good. Oh yeah, and so since I'm a physicist here, there's one other property that's very important for physics that I want to mention, and which is not exploited very much, and is also very important. So we have sort of, don't know what to call them, but asymptotic factorizations. So now we take any subgraph of G and now let G mod gamma be the graph obtained by contracting all edges in gamma. Now be careful here. So earlier I had a different notation, which was G double slash, and that notation meant that if you had a loop, a graph with a loop or tadpole, it gave 0. This notation is different deliberately because we can contract tadpoles and it's not 0. It's just the naive contraction of edges. So if we have, let's just do this graph mod E is that. So you just take the subgraph and you delete all the edges and identify all the vertices to one point. Okay, so that's why I use these different notations to avoid confusion. And then the theorem, which is not so well known, is that the graph polynomial it wants to factorize as the product of the subgraph and what's called the quotient graph, where you contract everything in the subgraph. But it's not quite true. There's an error term, remainder term. This is the remainder, and it's given by the property that it has degree greater than h gamma in the variables alpha e for e and gamma. So what's happening here? This degree h gamma in some variables. This has degree hg mod gamma in the remaining variables, and these things all have higher degree than this term. So if you would sort of expand, do an expansion where you think the alpha e for e and gamma are small, this is the leading term, and then you get higher order terms. So to make that a bit more clear, let's do a couple of examples. Yeah.
Do you mean that every monomial has degree higher?
Yes. Every monomial. So every monomial here is exactly homogeneous of degree h gamma in these variables. Every term here is exactly degree h gamma or more. But it's best to explain it on an example. So let's take this graph. And we computed this the other day. Psi g equals alpha 1, alpha 2, is alpha 1. No, it's not. Alpha 1, alpha 3, alpha 1, alpha 4. It's alpha 2, alpha 3, alpha 4, plus alpha 3, alpha 4. So let's take the subgraph 3, 4. And then the quotient G mod gamma is where you contract 3, 4 down and you get 1, 2. And the formula says that psi G equals the graph polynomial of the subgraph. So that's alpha 3 plus alpha 4. So this is psi gamma. Then times the polynomial of the quotient, alpha 1 plus alpha 2, plus remainder term, which is alpha 3, alpha 4. So you see, for the subgraph with edges 3, 4, this term is of degree 1 in alpha 3, alpha 4, but this is quadratic. It's degree 2 in alpha 3, alpha 4. So in other words, if you let alpha 3 and alpha 4 go to 0, you multiply them by some scalar, then this will be, you multiply them by epsilon, this will be order of epsilon, this is order of epsilon squared. So in the limit, as alpha 3, alpha 4 go to 0, it actually factorizes. That's why it's called an asymptotic factorization. And yes.
That's what we were talking about yesterday about integrals.
Yeah, exactly. So that's how you can prove. You can use this to prove the Weinberg theorem by studying the limiting behavior. Certainly, you can see that why the divergence has to happen from this formula. That's quite right. Converse is a bit more tricky. Let's do the same example, but now let's take gamma equals 1, 2, 3, and so now G equals, G mod gamma is now just a tadpole, and so now we find that psi G equals alpha 1 plus alpha 2 plus alpha 3 times alpha 4. So this is psi gamma, and this is psi G mod gamma, plus something. Alpha 1, alpha 3, and I can't see. So alpha 2, alpha 3, thank you. I think that's right. This is R. So this is kind of amazing because if you think about it, it says that if you know this factorization, if you knew that this graph polynomial for this small graph and for this small graph, you can reconstruct the whole of the graph polynomial up to some terms. Okay, so from this formula you get 4 out of the 5 terms. There's one you don't know. And from this formula you get 3 terms up to something, but 3 different terms. And you can see that in fact you can reconstruct the graph polynomial completely. And you can ask the question, which polynomials satisfy these types of factorization formulae? And in fact, it essentially uniquely characterizes the graph polynomial. There are very, very few ways in which you can do it. I mean, you can multiply everything by a scale. See, it's still you can multiply by something, but it essentially characterizes it uniquely. And this property is really important. In physics, it's used in the theory of renormalization in some sense. It's essential to renormalization, but it's a much deeper fact it's a more fundamental fact than the existence of the theory of renormalization. And it has some important geometric consequences. I won't have time to go further in that direction. But it's something that's not, in physics, it's not fully exploited. So I've hoped to persuade you that these, even if you're not interested in physics at all, that these graph polynomials are very natural from a mathematical point of view. Because they have all these properties, these combinatorial properties, these nice factorization properties, and this property of being the determinant of Laplacian. It's a very natural construction. Okay, so now I want to move back to some number theory to define combinatorial invariance using this. So I'm now going to talk about finite fields. So let P be a prime, and then for every prime power, there is a field FQ with Q elements, which is unique up to isomorphism. So when n is 1, Fp is just z mod pz. But it is definitely not true that Fp squared is z mod pz squared. To get Fp squared, you can construct it as follows. You let R in z mod pz such that R is not a square. So it's a quadratic non-residue. It's not a square mod p, let's say, in Zp. Mod p. Then Fp squared you can take as a model for z squared is just z mod pz adjoined x modulo the relation x squared equals r. In other words, it's the set of numbers a plus b square root of r, symbols of this type where a and b in z mod pz. So if you've never seen this before, you can just focus on this case, or take this as a definition. You can multiply and add expressions of this type as you would normally, and you can show that you can also take their inverses if they're non-zero. So you get a field. Okay, so armed with this, we can talk about counting points, which is a lot of fun. Counting points. So let f be a polynomial in n variables with integer coefficients. It doesn't have to be homogeneous, but it's very important that the coefficients be integers. And then for every prime power, we can define a symbol fq to be, the number of zeros of this polynomial. So it's the number of elements xn in fq such that f of x1 xn is 0. This is of course in fq. Okay, so given some elements in this field, we can add them, we can multiply them, and so because f has integer coefficients, we can compute any polynomial in any elements in fq. And we want to know how many of these q to the n possibilities gives us 0. So it's, in other words, it's the number of solutions to f equals 0 in fq to the n. And this gives us a map in prime powers q. For every power of a prime number, we get an integer. And so, for example, this is a great idea. We can, it's very important in number theory. But we can apply it, or x, e.g., we can apply it to graphs. So if we take G a graph, we can define G, Q to be the number of points over finite fields of this graph polynomial. And so it gives us a map from graphs. If you have a graph and a prime number, a prime power, you get a number, an integer. And so we get a very strange type of combinatorial invariant on graphs. And it's going to get stranger. Yes?
For a lot of people here, probably n means positive integer.
Ah, thank you. Yeah, you know, because I'm half British and half French, they have different conventions. Years ago, I just gave up trying to know which was which, so
0.
let me put that. And I never know what this symbol means. Thank you. It's different in every language. Okay, so this is something we can compute. And just finally, let me show you. Let's look at the graphs we had the other day. I'm going to write down some invariants. So we had a wheel with 2 spokes. The IG was 6 times zeta of 3. So I explained to you the weight of a multiple zeta, that's 3 in this case. The number of edges here is 6, so 6 minus 3 is 3. And with a computer, for example, you can compute this polynomial. Well, it's not necessarily a polynomial, but it's a function. As a function of q, in this case, it's a polynomial of q, and it's this. In fact, there's a closed formula for graphs of this type. The next graph we had was this, and the residue was 20 zeta 5. The weight is 5. Here we have 8 edges, so 8 minus 5 minus 3 is 5. And here it's something q to the 7 plus 3 q to the 5 minus 6q to the 4. And then we had this two-vertex join graph. And it gives 36 zeta 3 squared. The weight of this is 6. And the number of edges here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 minus 3 is 7. And here we have q to the 9. Okay, so we notice a couple of things. In general, the weight seems to be equal to the number of edges minus 3. But something funny happens here. This is what we call the weight drop, where the weight is less than this EG minus 3. You can show the weight is always bounded above. If it's a multiple zeta value, the weight is always less or equal to, and sometimes it's strictly smaller. And you notice here that these are all polynomials in Q. And so then Kontsevich asked this question in the 90s. Is GQ polynomial in Q for all graphs G? And expecting the answer yes, because this is somehow loosely related to the question of whether these integrals are multiple zetas. It's very loose. It's not directly connected, but it's a similar type of question. And then so combinatorics looked at this. So Stembridge in 1998 showed that it's true yes for all graphs with at most 12 edges. And I'll have time to explain the method. Very far behind.
But it's not correct
it's not true.
For any polynomial. Yes.
How do you mean?
If you fix any polynomial.
Oh no, you don't get every polynomial. No. You get very specific, very special.
But in general case, it's easy to understand that if you have polynomial, you have such polynomials which the
polynomial f
solutions is not polynomial.
It's not so easy to understand. But the classic example would be an elliptic curve, y squared minus 4x cubed minus ax minus b. So you pick a and b, and you count points over finite fields. In general, this will vary. It will not be polynomial
way.
Sorry?
In non-polynomial way.
Absolutely non-polynomial way. Mm-hmm. It's not so easy to see, but being polynomial is true for things that are somehow very linear. So here we've got a cube. For quadratic equation, it will be linear, but for a cubic equation, it'll almost never linear. But it's not so easy to see. And this is related to modular forms and all sorts of deep mathematics. What are the points on something like this? It's true. For general f, you can get extremely complicated functions, and they're not polynomial. So Belkany-Brosnan quickly, in 2003, in fact showed that these point counting functions for graphs are general type. So in particular, they showed the false for G with huge vertex degrees. So the degrees have insane numbers of edges coming out of them. And more importantly, they showed that GK is of general type. So it means that if you pick any polynomial, as you said, and look at the point counting function, then you can find some graphs in which it will appear somehow as a combination of their point counting functions. So the opposite to this question is true. It's as general as the point counting functions of all possible polynomials. But at the time, it was still thought that the graphs which actually come from physics, simple graphs, should still be polynomial. And that's something myself and Oliver Schnetz did in 2012, I think. We found we even found an explicit planar physical counterexample. So it's a graph you can draw. So starting from, I think, 18 edges or 17, 18 edges, something like that. So anyway, so it's just not true. But it's somehow, this point counting function is somehow measuring the complexity of the graph in some subtle way. So I don't have too much.
Is it related to this problem to the representativity in terms of zeta function?
Yeah, it's loosely connected. So I'll say in a minute. It turns out, I'll say in a minute how it's roughly connected. I'm a bit short of time. I was going to explain how it's possible to compute these sort of formulae, to compute the points of infinitely many finite fields at the same time. So here this gives a computation of fq for all q. Maybe I could hint at that briefly. Yeah, okay, so there's a sort of calculus you can do, which is good fun. I'll leave all this as an exercise. But if you have n polynomials, let me say n, in x1 up to xn, then of course you can count the number of points which are solutions to all these polynomials. For all I. Okay. And then there's some lemmas you can prove, which are great exercises. I'll put in black. So the first one is if you want to look at the solutions, the zeros of the polynomial f times g. If you have two polynomials, then the product vanishes if and only if one or the other or both vanish. And so you get either the solutions where one polynomial vanishes, where the other polynomial vanishes, and we've double counted where both polynomials vanish. So you can prove formulae like this, and you can check that if f is linear in one variable, so where f upper 1 and f lower 1 do not depend on alpha 1. So I've written alpha, so I mean x1, x2. So if we assume that the polynomial is linear in x1, then there's a nice formula which I leave as a great exercise, that fq equals f upper 1, f lower 1, q times q, plus q to the n minus 1 minus f1 q. This is a great exercise. Essentially you say either this polynomial f upper 1 vanishes or it doesn't. If it doesn't vanish, then if f is going to vanish, this is going to uniquely determine x1. So let's do, if it does vanish, then x1 can be, then for this to vanish, f lower 1 has to vanish, and x1 can be anything. So that means f upper 1 and f lower 1 vanish, and x1 has q possibilities, and that gives this term. And then if f1 is non-zero, he gives this term. But that's a great exercise. Okay, so then it turns out after much thinking about this problem that in fact most of the information in this point counting polynomial is junk. So it's just not interesting. So we observe, so it should be blank, observation, that GQ is always congruent to 0 mod Q squared. And you see that in these examples. It's always begins in Q squared, and here it even starts in Q to the 5. And it turns out we can throw all this stuff, we can throw away. It's just junk. It's not related to anything. Okay? And so what we did is we defined a much better invariant, which is much more interesting than the graph polynomial. Let me delete this. So we define, so we call this the C2 invariant. So since the point counting function is always divisible by Q squared, we define C2 brackets Q G equals point counting function mod divided by Q squared, and then we look mod Q. And this is the right thing to do. And so as Q varies, this gives a sequence of numbers mod Q for all Q prime power. Okay, so this seems like a strange thing to do. But if GQ is a polynomial in Q, then C2 is the coefficient of Q squared. And that's why it's called C2, is the coefficient of Q squared, modular Q. But it might not be a polynomial in Q. And in fact, if this thing is not, and this thing jumps around a lot, then it implies that this GQ could not be a polynomial. So if it were a polynomial, let's do it. So C2 here, we look at the coefficient of Q squared, it's just minus 1. For every Q, it's always minus 1. Here for every Q, it's always minus 1. And for this graph, it's 0, because there's no coefficient of Q squared. And so this minus 1 means it's, for every Q, it's the constant function minus 1, minus 1, minus 1, minus 1. And so C2, it contains just the right information. So this is a very subtle invariant of a graph. And I will explain to you briefly why it's related to this question, how it's related to the residue.
If it is a polynomial in Q, but contains a constant term or a first power of Q,
we always know that it's...
It never does. For the graphs, it's always divisible by Q squared. But if you wanted to define something like this for an arbitrary polynomial, you would just take polynomial mod Q. It's just, in these examples, there's always this shift. It's always Q squared times something. And you can prove that by using these formulae inductively. It's not very difficult. But to show it's divisible by Q is not difficult. To show it's divisible by Q squared is more tricky. It's like the first. If you go from the left, it's the first interesting non-trivial piece of the graph of the point counting function. So why is this important? Well, you may have seen on the example that C2G vanishes if and only if in some technical sense IG has weight drop. It detects when a graph has weight drop. So this requires some qualification here. If a graph has a subdivergence, this is an important physical concept. So the number of edges in the graph is twice. So a strict subgraph where it has edges more than twice the loop number, then the C2 invariant vanishes as well. And here's another conjecture. If two graphs have the same residue, then they must have the same C2 invariance. And morally speaking, the C2 invariant somehow detects some piece of information about this integral. So armed with this conjecture, I gave a list of properties of these residues last time, and therefore you expect the C2 to have the same combinatorial properties. And what happened is that these were proven one by one. Some of them are very easy. Duality took longer, but the completion is still open. So conjecture, if completion of G1 is isomorphic to G2, then C2 of G1 equals C2. And this was recently proven by Hu and Yates and Hu and Panzer. This was for Q equals 2, and in this case for Q equals P prime. But for prime power, it's still open. And I'll talk a little bit more about this. The techniques I will develop will give, I hope, a proof of this shortly. And finally, to have a little bit of time, or should I?
Yes, you do.
Do I? Just a couple of minutes. There's something I want to say about. So this idea. So if we just look at Q primes, so Q equals 2, and not forget prime powers, then we have basically an infinite sequence of invariants of graph. And they lie in Z mod 2Z, Z mod 3Z, Z mod 5Z. And each individual C2 invariant, it doesn't contain much information. C2 is either 0 or 1. C3 is either 0, 1, or 2. But if you take all of them together, it contains a huge amount of information. And this general idea of counting points over finite fields and then reducing modulo a prime is very interesting. So let me say something that's very classical about this particular idea, because it's something we've been discussing today, and it's a fun thing. So counting points over finite fields in general is very difficult. It's easy to define, but in practice it's difficult because you have infinitely many fields to think about. So here's a theorem. So let f in Z1 xn be homogeneous. It doesn't have to be homogeneous. of degree n. So it's a polynomial whose number of variables is equal to the degree. And we let q equals p to the n. And we have fq defined as before. Sorry, I don't want to do that. I'm just going to do, this is futuristic, I just want, pen doesn't work. Let's try q. Let's just do q equals prime. So we have fp is in n positive equals the number of solutions x1 xn in fp such that f of x equals 0. Okay. Now let delta m equals coefficient of x1 xn to the m in f of x1 to the n. So we'll discuss this more tomorrow. Then there's a theorem, which is classical, but I don't know who it's due to. It's a variant of the Chevalier-Warning theorem, but it implies what's called the Chevalier-Warning theorem. I think it's certainly in a paper by Axe in '64, but it's probably older than that. And the theorem states that if you want to count the points, so the number of solutions of this polynomial fp is congruent to delta minus 1 to the n minus 1 delta p mod p. I don't have time, but it has a very, very easy proof. It has essentially a one-line proof. Very beautiful. 2 lines, okay. Maybe we can talk about that another time.
P minus 1.
Oh, thank you. Delta p minus 1. Thank you very much. Delta p minus 1. So it gives you some idea of where these point count. It means that the point counting function can be very wild, but the point counting function mod p is something very easy to understand. You just take your polynomial, raise it to p minus 1, and read off just one coefficient. And that gives you the point counting function mod p. And you can do that with, for example, the elliptic curve I had earlier. You can make it homogeneous and look at something like 4x cubed ax z squared minus b z cubed. So a and b, you fix your favorite integers. Just choose some a, b, z, and if you want to count the points over a finite field of this thing, well, you just take the whole thing to the power p minus 1, and you look for the coefficient of x, y, z to the p minus 1 in this. And you can see it's going to be some multinomial coefficient. But the point is that the multinomial, or some binomial or multinomial coefficient, the point is that multinomial coefficients mod p can behave very complex ways.
The sum of
A sum of multinomial coefficients. And we saw this at the first lecture, this Apery sequence. I gave a formula as a sum of binomial coefficients. I gave something like this. And these ideas will all come together and in the next lecture. We'll connect everything together. I'll stop there for today.